Assalamu alaikum wa rahmatullahi wa barakatuh. Okay, so let's begin the class today. So we'll start with the feedback compensation, the approach 2, the second approach. Already we discussed the first approach in the last class. That was somehow similar to the cascade compensation. So now this one is slightly different. In this approach, designer is actually allowed to design two loops separately. So minor loops transient response is designed separately than the closed loop transfer function. And if you look at this block diagram, then you can see that your this feedback one is basically your a component or a transfer function that can be considered a transfer function of the forward path. So this one is also can be considered as a cascade component of your whole transfer function. So eventually, in the overall transfer function, it is not appearing in the feedback. Okay, so from that aspect, we can consider this one to be as a forward path transfer function. And we're trying to change the poles of that one by adjusting the gain of your minor loop. So in our minor loop, there may be K1 as well as KF. So by changing these two, the one that is available actually, based on that, we'll try to adjust the poles of that loop. Okay, so which is a cascade component in the forward path. So now these poles that we have identified or obtained after adjusting the gain of the minor loop, that pole are eventually becoming the poles, open loop poles of the entire closed loop transfer function. So whatever the status of the pole that you have obtained, using that pole, we'll try to plot the overall closed loop transfer functions root locus. So eventually you have to draw two root locus for this scenario. One for the minor loop, designing the minor loop using the root locus, and based on that, whatever the poles and the zeros that you're obtaining, that poles and the zeros have to be the initial point of your overall transfer function. So this is what is I've been trying to explain here, actually, in other words, rather than reshaping the root locus with additional pole of 0. So we are not introducing any pole of 0. That was the case in case of the cascade. We are trying to just change the gain of the one loop. Using that one, we're changing the poles, times pole, only by the adjustment of the gain. Okay, so this is what we are trying to do. And finally, that closed loop poles are set as an open loop, and then you just apply the cascade one. So what we're trying to say that will be explained in detail in your example 9.8, minor low feedback compensation. So this figure 9.11, which is just simply a given system, which is this one, and a design of the minor loop adjustment was being shown in your figure 9.b, which is this one. So basically, this portion will be dealing with first. Okay, once we are happy with that, so basically in this one, K1 is not available. So only the thing that is we are changing is KF. And once it is done, then we'll go for overall closed loop transfer function, the whole system that will be based on the variation of K. So first one is based on KF, and the second one is based on K. This is how we are going to go for the designing of this system. Okay, so now let's start with the problem. First of all, we'll deal with the minor loop. So the minor loop is simply this one. Just you can have your, not necessarily you have to show what signal coming, just your G of S forward path 1 as well as your feedback 1. So that is what we are trying to have. So 1 by s plus 5 s plus 15. And KFS. So now this is your G of S and this is of your H of S. So your loop gain or G of S, H of S, based on which we actually plot the root locus, that is becoming for definitely for it, this is your minor loop. So G of S, H of S is now KFS, and then you have S plus 5 and S plus 15. So you can see S is common and can be cancelled out, but it should not do that because it will have an impact on your transfer function. What does it mean is that the zero here is of the feedback zero. So that one may not go to the overall transfer function. So what does it mean is if you try to find out the overall transfer function of the minor, that is your G minor loop transfer function. If you try to figure it out, then 1 G of S, that is 1 by S times S plus 5, S plus 15, then 1 plus KF. You can just keep the KF later on where the HFs. So it's up to you. So 1 by S, S plus 5, S plus 15 multiplied by K of S. So if you simplify that, we already solved this in the last class, the approach 1. So it gives you something like this. S by S square plus 20 S plus 75 plus KF. So as you can see that zero is not appearing in the zero of your overall transfer function. So that is why cancel on these two should not be a wise thing to do. So keep them as it is, and how they will impact in the root locus, let's try to see that. So at location 0, at location origin, you also have a pole and a 0. So our root locus will have a, and also whether you have noticed the problem carefully or not. So minor loop has a damping ratio of 0.8, and your closed loop, which is ultimately our system's damping ratio, is 0.6. So using 0.8, we are adjusting the poles of the closed loop, feedback, and then for the closed loop, we'll be using the damping ratio of 0.6. So now, how many pole and zero you have? You have 3 poles, 1 0, and 2 pole at the same, 1 pole and 0 in the same location. So ultimately, this is what you have: a pole at the origin as well as a 0 at the origin. So this kind of pole is also known as a stationary pole. Because of the pole 0 same location, this pole cannot change its position. So stationary pole. Okay. And the other is at -5, at -15, somewhere here. Okay, so how the root locus will look like? Basically, it is something similar to having a 2-pole scenario. So at -10, they will be merging together. Then one will be following the upper line towards infinity, and the other will be following the lower line towards infinity. So this is what we know from our idea of root locus. So what is next? We have to find out the intersection line of this root locus with your zeta line that is given. So your zeta line calculation is inner loop or minor loop. Zeta is basically 0.8. So zeta is 0.8. So your theta will be cos inverse 0.8. That will give you around 36.869. And the angle will be basically 180 degree minus theta. So that will be around 143.13. So if you plot the point, you're going to find some line like this. Okay, so probably a ruler will be wiser thing to use. Okay, so around 36 degrees. So something like this should be the scenario. So this intersection point with an angle of 143.13 approximately, that will give you, according to the book, we're just following their data. So minus 10 and plus J 7.5. So also from this one, we can calculate, since our minus 10 is not changing. So minus 10 is basically minus zeta, sorry, zeta omega n, which is nothing but minus sigma, sigma d. Okay, so already we know the value of zeta. So from that one, we can also find out what will be the value of omega n. So this will give you around basically 10 by 0.8, ultimately 12.5. Okay, so now this is three-fold scenario that we are obtaining from this minor loop gain adjustment. So what we need to know is for what value of kf we are going to that point minus 10 plus minus 7.5. Why that is important? Because your transfer function requires a value of kf, which is supposed to be placed here. So we know the formula for that. The formula for that is basically kf equal to, which is same as gain k in case of the root locus, which is a pole length divided by product of the pole length divided by the product of the zero length. Product of the zero lengths. So since even though we have a pole and zero at the origin, their length will be exactly equal, so we can avoid that. We just can take the other two, that is the distance between these two. This one can be called as L1, and the distance between that one has to be L2. Their length has to be equal as well because of the fact that they're equidistant from your minus 10. So basically L1 times L2 has to be your distance, L1 times L2. And L1 and L2 can be calculated as height base square, that is 10 minus 5 whole square plus 7.5 whole square times 15 minus 5 whole square plus 7.5 whole square. So ultimately, it will be around 81.25. So this is first part. By adjusting the gain of your F, we figure out what will be the location. So 3 locations we already figure out. One location is pole at the origin. So this is 1, which is stationary for minor loop. And then you have one pole here at minus 10 plus J 7.5, and the other one has to be the other side as well. So minus 10 minus J 7.5. So this will be 3 location, and this will be the starting point or open loop pole of your overall closed loop root locus. So we can say that G of S, H of S of G of S, H of S of your major loop will be A by S plus 10 plus J 7.5 S plus 10 minus J 7.5. Okay, so in this loop, we're trying to adjust the gain K. So now, for plotting that one, what we already have is the 3 location. So the result is also in there. Okay, so let's draw it somewhere here. So 3 location already we have pole at the origin. 0 will not come because 0 is not a function of the closed loop transfer function. We already plotted that one. So this will be 3 location basically. So minus 10 plus J 7.5 minus 10 minus J 7.5. So how the root locus should look like? Definitely this segment will be on the root locus. This is one of our real axis segment. This will be on the root locus. And other 2, basically also how many infinite lines should be there? There should be 3 infinite lines because of the fact that we have 3 poles only, there is no 0. So 3 infinite lines should be there. So based on that, we can find out our sigma A. Sigma A is summation of the poles minus summation of the zeros. So first pole at 0, then second at minus 10, then minus 10, divided by pole minus 0. So 3 poles, no 0. So ultimately it will give you a minus 6.67 around. And your theta A, so angle of asymptotes will be twice k plus 1 pi by 3 minus 0. So twice k plus 1 pi by 3. So that will give you more or less these values are same. If it is 2 of them, then 90 degrees, 270 degrees, 3 of them, then 16, then 180 degrees, as well as 300 degrees. So for k equal to 0, 1, 2. So now, since we have complex poles, we have to find out the angle of departure. So say we want to calculate for this one. So this is our point of interest. So we have to find out all the angles, and that has to be this odd multiple of 180 degrees. So definitely this angle is 90 degrees. There is no question about it. And this angle, we already know the angle here, because based on that, we actually plotted our root locus zeta line. So that angle is around 143.13. So this is already known to us. So let's, based on these two, let's find out the angle of departure. Okay, so I'm just erasing those because of the fact that later on we have to, it will be easier if those lines are not available. So now your minus d angle that is at that particular point is minus angle of departure theta c, all basically your pole angles, so all have to be negative, and minus yeah, just for the sake of the formula, 180 degree minus tan inverse 7.5 by 10 height by base minus 90 degrees should be equal to your plus minus 90 degrees. So it's better to use minus 90 degree because minus 180 degree because all the angles are negative. So it will be eventually closer to the negative 180 degree. So that will give us minus theta d equal to minus 233.13 equal to minus 180. So minus theta d equal to minus 180 plus 233.13 around 53.13. So basically this will be minus here, or you can just subtract from 300, so 360 minus 53.13. So that will give you around 306.87. So almost 300 degree line will be there. So first of all, you have to draw your angle intersection point. So say around -6 over here, your intersection point, and one will be 60 degree line, and one will be 60 degree line. So the 180 degree line, you don't need to draw. You already have that in here. Okay, so somehow values. Okay, something similar to that, but somehow the ruler is not behaving as supposed to behave. Okay, so now next is the angle of departure. So angle of departure will be around 300 degrees. So around this line eventually. So this should be your angle of departure. Okay, so this should be your angle of departure somehow similar to this. So we can see that our poles will leave, the root locus will leave the pole with an angle of like this, then it will gradually follow a path like this. Eventually, you can also find out the geometric axis crossing that will help you to plot it more precisely. So something like this will be happening as well in the other side. Okay, so now this is your root locus. This is one segment, this is another one, and this is the other one. So what they're trying to figure, what they're asking you to draw next is basically finding overall transfer function or closed loop dampening of 0.6. So based on that, you will have find another zeta line, and that zeta line will intersect with your given root locus, and that will give you dominant second order poles. So our zeta for this one, the calculation of zeta is 0.6 And based on that, your theta is cos inverse 0.6. That will give you around 43.13. Okay, so oh, sorry, that will be actually 53.13. 53. So now your 180-degree minus 53.13 will be around 126.87. So 126.87 line you have to draw. Okay, so 1 minus 60. So 180 minus that value 53, that should give you around 126. So this is your new zeta line, which is around 126.87. So this is your operating point now. So which is based on the changing the gain K. Okay, so this is your new operating point. And according to the book, the intersection point is around -4 point. So these lines you have to figure out from the graph, whatever the value comes. I'm just taking the book value because I'm trying to match the result with their result. But we just plot it in the graph, whatever the intersection you get, that will be your result. So plus J 6.046. So this is the point that we obtained for overall zeta of your 0.6. Okay, so this is the intersection point. Now next is calculating for which value of gain K, because the minor lobe we have changed the gain KF, or the major lobe we have to change the gain K. So the existing poles are actually one is here, and the other one is here. So from that one, we have to find out the distance of the pole lengths and the zero lengths that will give you the gain K. So the gain K, calculation of the gain K can be used as, because 3 pole length you have. So now K will be L1 times L2 times L3. Okay, so from the origin is simple. Just from the origin, just the coordinates that you are given, just make a square of that one. So 4.535 whole square plus 6.046 whole square. So this is your L1. The other one, the one that is closer, will be actually from 10.4, 10 minus 4.535 whole square, the distance between them. So 7.5 minus 6.046 whole square. And the other one will be additive because that is far away. So basically 10 minus 4.535 whole square. The vertical length will be added. So it will be 7.5 plus 6.046 whole square. So if you multiply all these, then you're going to get the gain K as 624.23. So this is your modified values of your gain K, for which we are obtaining that dominant second order point. So these are this is a procedure for dealing with this scenario. Now look at the results, comparison results. So if you look at this one, and the first one is the uncompensated one. So you check the result. This is your dominant second order pole. I have just solved you the first part of it. Actually, in the class, I have shown you how to solve the compensated one first, which is supposed to be very easy, and which is the same as before, whatever we have done previously. And based on that, you do all repeat all the calculation. Now, the compensated system transfer function, as you can see how you have 250, 156 here, it is basically your 75 plus KF. So we already figured out that the KF value is 81.25. So if you add those two, then you're going to get your compensated systems plant and the compensator. This one we already calculated. We have obtained from the graph. This one we calculated. This one is given, and omega n can be calculated from sigma d equal to, that is 4.3535 divided by your 0.6, that will give you 7.558. And percentage overshoot is based on the zeta, so you will be able to calculate that from the book. Example, and your settling time is also just applying the formula by sigma d. So we know the value of the sigma d, and from that one you'll be able to calculate, which will be around 8.882. And your peak time is pi by omega d. So put the values. Ultimately, it will give you around 0.52. So now in your KV, so KV, for finding the KV, you have to plug in the value of K here. So it's already calculated 624.3. So basically, limit S tends to 0 as G of S. So ultimately, it will be limit S tends to 0. S is getting cancelled out. So 624.3 by S squared plus 20S plus 156.25. So ultimately, 624 divided by 156, that will be the result, and which will be ultimately around 3.996. And what is our steady state error? Steady state error is 1 by KV, so ultimately 0.25. So next thing you have to figure out is the other pole. So other pole or third order pole, how can I figure out that one? Basically, what we are trying to do is to figure out what will happen to this pole. So whenever your gain is 624.3, then where it will be? So that location we are trying to figure out. So this is what is being called as other pole or third pole. So now you have to find out all the lanes. So approximately say this is your X, location is X, and this is your one of the original pole, or the other original pole is this and this. So you have to find out the distance from that. So all the pole lengths, 3 pole lengths, has to be equal to your 624.3. So this is slightly different scenario now. So your gain A, which is 624.3, will be the location of from the first one, which is at the origin, which is X. So there is no doubt about it. What about the other location? Now it's becoming slightly tricky. So it has to be, say, 10 minus X square, and the real portion is not changing, the height is not changing, so it has to be 7.5 whole square. Okay, so this should be your one length. The other length has to be also same because they are identical. So 10 minus 7. And you can give minus 7.5 whole square, but eventually there is exactly same. So x times 10 minus x whole square plus 7.5 whole square. So that is your formula. And now we can solve it, or using trial and error, you can find out the value of x. That will give you 624.3. Eventually, you're going to see that the value of x will be around, according to the book, minus 10.93. Plus, we have to comment on our second order approximation, so whether it is valid or not. So uncompensated systems real part, as you can see, which is around 2. The dominant second order pole is minus 2, and the other pole is minus 16. So it's more than 5 times. So your second order approximation is valid in this case. But in the other case, as you can see here, it is around 4.5. It is minus 10. So it's very close here. So whatever the calculations we're doing here, so they may not be accurate. So that is why we have to mention the fact that our results has to be verified by simulation, or whatever the values or the changes we have to accommodate according to our simulation. So this is your second approach of designing the feedback. The first approach was similar to the cascade, and this approach is basically based on 2 separate root locus design. So we haven't introduced any pole and zero. We've just changed the location of the poles of minor loop. Then based on the poles of the minor loop, based on the gain of the minor loop, whatever the pole we have obtained, based on that we have designed the major loop. So 2 separate gain adjustment we have done.